All right, I mean, it can't be that hard, right? You took Calc 2 and you know how to integrate a little bit. And you see tangent within negative 1/2 power x, and hopefully you're comfortable with that being equal to 1 over the square root of tangent of x. And you're like, all right, so there's some little trick, and you do that little trick and you integrate this, right? Turns out no. Turns out this problem is a mess. Turns out that the way it's written right here, there's nothing I can do other than kind of add some stuff in. I'm going to put a secant squared x in here. Why? Because the derivative of tangent, as hopefully you know, is equal to secant squared x, and I'm going to have to do a little u substitution. And you're like, well, you can't just throw a secant squared x up there. It's going to change the value of this quotient. All right, fine. I'll throw one on the bottom too, secant squared x. And you're like, now you're messing everything up. This ain't going to work at all because only one of these two can be my du in my u substitution. Well, what I can now do is take advantage of the Pythagorean identity. Again, hopefully you know this. Sine squared x plus cosine squared x equals 1. So if you take each of these three terms and divide them by cosine squared x, you get this version of the Pythagorean identity. And this one will be really handy because I can rewrite this integral as secant squared x divided by the square root of tangent x times tangent squared x plus 1, just doing this little substitution that I have over here. And the reason you might want to make that change is because now a u substitution where u equals tangent of x is going to work out really nicely. My u substitution takes me here, which frankly doesn't look a whole lot better, but trust me, we're kind of heading down the right path, although it is a long and nasty path. The next challenge to deal with is this radical here. Informally speaking, radicals don't work out that nicely when you're trying to integrate. So what I want to do is another substitution, maybe a v substitution, because why not? And what I want to do is choose v so that my dv will get rid of this 1 over the square root of u. So I'm going to choose things so that this works out really nice. Let's see, let me fill in the pieces. How am I going to get it? How am I going to get 1 over the square root of u as dv? Well, I guess I would have to let v be equal to the square root of u. And you're like, wait a minute, that doesn't check out. If v is the square root of u, kind of u to the 1/2 power, you bring that 1/2 down in front, and then you get u to the negative 1/2, which looks like this, except you have that 1/2. That's true. So there should be a 1/2 here. Fine, I'll put it over here, multiply both sides of the equation by 2, and now I can get rid of everything that I need. Conveniently enough, my square root of u is now gone. And then note, because v is the square root of u, v squared equals u, or v to the 4th equals u squared. So instead of u squared plus 1, I got v to the 4th plus 1. That gets me here. You're like, oh, cool, and then we're almost done? Like, that's something? No, that's nothing that we know of. What I now have to do is some algebra, some pretty complex algebra. I got to deal with this v to the 4th power plus 1. And essentially what I want to do is I want to factor that. I want to write that as a product of two different terms. And so you can think about it for a minute. What is v to the 4th plus 1 if you factor it out? Come up with your answer. Yeah, it's just v squared plus 1 squared, right? No, not at all, right? You can't distribute an exponent down into these terms like this. You think FOIL if you want. This does not equal this, right? This would have an extra term. I'd get v to the 4th plus I'd get 2 v squareds plus 1. So in order for this to be equal to this, I have to subtract those 2 v squareds. Now I guess it works out. Although now it's not factored, right? I was hoping to write it as something times something. Because if you're kind of looking ahead, if we can write it as something times something, we can use partial fraction decomposition. Well, good news, this is a square. It's v squared plus 1 squared. And guess what? This is a square also, right? Less apparent perhaps, but still a perfect square. I could write it as the square root of 2 times v quantity squared. And now it is something squared minus something squared. It's a difference of squares. And hopefully you know a formula for how to factor a difference of squares. Think x squared minus 9 being x plus 3 times x minus 3. So I factor this as a difference of squares, and that leaves me with this product here, which I can then substitute into my integral here. Note, I pulled the 2 out in front because that's something you can do. One less thing to look at. And what I've managed to do is rewrite this integral as this integral. And it looks like it's getting worse, but really it's not, because this integral lends itself really well to partial fraction decomposition. So the idea with partial fraction decomposition is I want to rewrite this quotient where the denominator is itself a product as the sum of two different quotients, the denominators being those factors in the product. And because each of those denominators are quadratic, I can't just put an a in the numerators. I need to put something that is linear, so av plus b and cv plus d. And essentially what I have to do is solve this equation to figure out what a, b, c, and d are equal to, and then I can replace all this mess with this mess. So what I'm going to do is I am going to multiply both sides of this equation by this denominator here, And informally, that's going to cancel all this out and leave me with just a 1. And then over here, I'll be left with the numerator here times the denominator here plus the denominator here plus the numerator here. And that's what I have on this line here. And now I'm going to FOIL if you want, although that acronym doesn't really work because there's a trinomial over here. But expand this all out. Get rid of the parentheses if you want. So you expand this all out and you get here, which looks horrible, but really it kind of implies, 4 different equations. So matching coefficients, on the left-hand side, I have nothing in front of my v cubes. And on the right-hand side, I have an a in front of a v cubed and a d in front of, a c in front of a v cubed. So a plus c must equal 0. Similarly, for my v squares, I get this equation. My v's, I get this equation. And for my constants, I have a 1 on the left side and a b plus d on the right side. So I have a system of 4 equations with 4 unknowns, so I can solve that system of equations. So because a plus c equals 0 in this equation here, this a and this c I can change into a 0, which leaves me with this equation. And because b plus d equals 1, this b and this d I can change into a 1, which leaves me with this equation here. So now to finish this up, a plus c equals 0 implies that c equals negative a, and b plus d equals 1 implies that d equals 1 minus b. So I can take this equation and I can change the negative c into a positive a, which gets me this. And I can take this equation, I can change the negative d into, or I guess I can change the d into 1 minus b, and that gives me this equation. So then solving these equations, I have 2 of these a root 2 things, plus 1 equals 0. So 2a root 2 equals negative 1, so a equals negative 1 over 2 root 2. And over here, if I distribute this root 2, I have 2 of these b root 2 things, and then minus the square root of 2 equals 0. So 2b root 2 equals root 2, so b equals 1/2. And that's 2 of the 4 constants, but really I get the other 2 almost for free because a and c are opposites. I know that c must be equal to 1 over 2 root 2. And because b and d equal 1 when you sum them, if b is 1/2, d is also 1/2. And I have my 4 values that I solve for. So remember, the whole reason we solve for these 4 constants is they're the 4 values that make this equal to this, and presumably this is the preferable form to integrate. So what I can do is I can take my old integral, which was exactly the left side here was the integrand, and change that into the right side as my integrand, which is what I did in this huge mess here in green, plugging in for a, b, c, and d as they were solved for below. And you look at this and you've never seen something so ugly in your life, but note that it's not as bad as you think. A couple of comments here. If we made this 1 root 2 over 2 root 2 and made this 1 root 2 over 2 root 2, now I'd have a common denominator here in each of these 4 terms, and maybe I could factor that out in front to kind of clean things up. And now you notice that the derivative of the denominator here is exactly the numerator here, so we do another u sub and everything works out and we're done. Not quite. Almost though, right? The derivative of the denominator here is damn near what I have up here. If this were a 2 up to a constant, I'd be right. So I really wish this were a 2. And I got a 2 right here. I guess I could distribute that back in. But then the problem is then I have 2 root 2, and I want it to just be a single root 2, which isn't going to work out perfectly. But maybe there's something I can do. So I take this 2 and I distribute it back through. That makes this v a 2v, and that makes this root 2 2 root 2, which I write as 2 separate root 2's because that'll be convenient later on. And note I changed the sign on all this stuff in the numerator on this first term by pulling out a negative here. Same idea in the second term. I now have 2 v's and 2 of these root 2's that I write this way. And maybe now you can kind of see how this is going to unfold. This denominator here is going to work out really nice with another substitution, a w substitution, I guess, to take care of these first 2 terms in the numerator. This negative root 2, that's going to be kind of a pain, but I'll deal with that later. And then same idea over here, making a w, this denominator will take care of the first 2 terms, and I'll have to deal with the third one later. So in the spirit of that strategy, I will rewrite this as 4 different integrals. I have this 1 over 2 root 2 to deal with eventually, and then the first 2 terms in the numerator here, 2v minus root 2 divided by this denominator, plus, and you're like, it should be minus. Yeah, but don't forget about this minus here. Makes it plus root 2 over this denominator. And then same idea, I'll split this up into 2 different integrals, the first 2 terms and then the third term, to get me these 4 integrals right here. So taking this first integral and kind of solving it on the side here, I'm going to do this w substitution where w is the denominator, and that makes dw essentially the numerator. So what I end up with is the integral of 1 over w dw, which is just the natural log of the absolute value of w. And virtually the same thing works out over here, except now when my dw is equal to 2v plus root 2 my numerator, because my w is v squared plus root 2v plus 1, which works out really nicely. I again end up with 1 over w, which when I integrate that gives me the natural log of the absolute value of w, which I substitute in, and I take care of these two here. And for this second and fourth integral, the trick is to recognize that what you have here looks a hell of a lot, maybe not a hell of a lot, looks a little bit like the derivative arctangent of x, which is 1 over x squared plus 1. So if I could just make this 1 over x squared plus 1, I'd be in really good shape. You can almost see it, the root 2, I could pull that out in front, and then I would be left with 1 over v squared, kind of like x squared, plus 1. And then over here, I pull out the root 2, and I'm left with 1 over v squared plus 1. I'm in really good shape. But you're like, what about this negative root 2? Well, I can take care of this negative root 2v by completing the square. I can rewrite the denominator on this line as I wrote the denominator on this line. And you're like, wait, does that make sense? Oh, because you'd have to FOIL, and v times v would give me v squared, and the o and the I in FOIL would get me this negative root 2v. Yeah, I guess that checks out. And the L in FOIL, negative root 2 over 2 times negative root 2 over 2 would be positive. Wait, no, that wouldn't be positive 1. Shoot, that would be positive 1/2. All right, no problem. Just throw a plus 1/2 here, because then the plus 1/2 from this and the plus 1/2 from this get you the 1 that you wanted here. And the same logic will work over here. If I complete the square on this side, I would just need a plus 1/2 to make this denominator the same as this denominator. And you're like, but there's a problem with that. A minute ago, you told me we were going to try to get something like this arctangent formula, and the arctangent formula doesn't have a 1/2 right here. It has a 1 right here. No problem. We can fix that if we multiply through a 2. So one way you can think about it is throw a 2 on the top and throw a 2 on the bottom, and the 2 that you threw up on the top factored out in front to make this 2 root 2. And then down on the bottom, this 2 is going to hit each of my terms, change this 1/2 into a 1, and this 2 will just sit here for now. Same logic over here. Now I can do that arctangent trick? Nah, because arctangent doesn't have 2 times something squared. It just has something squared. So I got to get rid of this 2. Oh, I'll just distribute it into these parentheses. Wait, I thought you couldn't distribute that into the parentheses because the parentheses are squared and the 2 is not. True, but if instead of viewing it as a 2, I view it as square root of 2 squared, then I can take that square root of 2 and distribute it into these parentheses because this is squared and this is squared. So after distributing this root 2 into the parentheses, things are set up perfectly for a substitution. What I'm ending up with here in my integrand is 1 over something squared plus 1, which again was what I was shooting for here. I can just do a substitution and I'll be left with arctangent. So the specifics of that, we're going to let w be equal to root 2v minus 1 on this side, and on this side the same idea, except now w is root 2v plus 1. And either way, that makes my dw root 2 times dv. In other words, 1 over root 2 dw equals dv. And we go and we substitute that in, and we end up with 2 times the integral of 1 over w squared plus 1 dw, exactly what we were hoping for. That integral evaluates to twice the arctangent of w plus c. And so I just go plugging in my respective w's, root 2v minus 1 and root 2v plus 1, and I figure out my integrals. So I'm essentially done with the calculus at this point. I take these 4 answers for the 4 different integrals that I was trying to work out somewhere here, and go plugging those back up into when I was working on those 4 integrals here. And that gives me this mess of an expression here, which is a good answer, except it's an answer in v. So v's were the square root of u, but really u's will end up being the tangent of x. We go and change all of our v's down here into square roots of u, and that leaves us with this line here. But then changing all my u's into tangent of x, I get this monster of an expression written in terms of x's. So just cleaning things up, 1 over 2 root 2 is the same as 2 to the negative 3/2 power. And then taking these 2 terms that have logs in them, I can use a difference of logs formula to rewrite this as the log of this mess divided by this mess, which is what I have here. That leaves me with the 2 arctangent terms. So I can cancel out the 2 in the denominator with these 2's here and call this 2 to the negative 1/2 power. And then I have arctangent of this mess plus arctangent of this mess. You probably simplify that somehow. I don't know how, at least not off the top of my head. And I'm kind of burnt out on this problem, so I'm going to call this monstrosity good here and end this video. So that is how you integrate this innocent looking problem